So before presenting the topics of the present discussion, let's make a few considerations about measurement in quantum mechanics. So there is an ambiguity among the postulates of quantum mechanics, as we state that an isolated system evolves as a unitary evolution. So it is continuous in time. But at the same time, we say that when we make a measurement, the state of the system instantaneously collapses into an eigenstate, and this process is not continuous. Then, as the measurement is a concept that is defined in the postulates, we don't know how quantum measurement works and when the collapse of the wave function happens during an experiment. Then it is not even clear how experimentally we can measure an operator, a quantum operator. Today we will not solve this fundamental problem of quantum mechanics, but we will give a description of quantum measurement that at least explains how experimentally we can measure an operator, the desired operator O, and then it will give us an operative description of quantum measurement that and what we mean by operative we will be clean later. But to clarify it, today we will not talk about what happens to the wave function of the universe when we make a measurement. This problem is accounted as the measured problem, and you can get only partial answers through interpretation of quantum mechanics. But today we will not talk about interpretation. So let's focus on the first question that we can reformulate as: how should we design an experimental apparatus in order to measure a desired operator O? In order to answer this question, we have to think the measurement as a process where an apparatus interacts with the system we want to measure. And the idea is that we will require some properties that the apparatus has to satisfy in order to measure the operator O, and these properties will constrain the interaction between the system and the apparatus. Then we can read these constraints as the way we should design the apparatus in order to measure this operator. But before getting this constraint, we have to show how concretely we deal with measurement inside our theory. And to do that in a simple way, we follow an example that is, so we consider a qubit, and we want to measure the operator sigma x. Now, in general, when we make a measurement, we have a macroscopic indicator whose orientation tells us what is the state of the system. And what is the most natural way of including this consideration in the quantum formalism? The most natural way is to consider that if we have a state that is plus state of the system times an initial state of the apparatus, the interaction between system and apparatus maps this state into a state of this shape, where A plus is the state of the apparatus corresponding to the orientation of the macroscopic indicator corresponding to the state plus of the system. And we can state the same thing for the state minus. So if we use the superposition principle, we have that a general state alpha plus beta minus is mapped by this interaction into a state that is alpha plus A plus beta minus A minus. So what happens is that the interaction between the system and the environment establishes an entanglement between the basis of eigenstates of the operator we want to measure and the basis of the apparatus. So if we make a projective measurement on the apparatus, we end up in only one of the two states, and so we can conclude what is the state of the system. here the state plus and minus are orthogonal, and while the state a plus and a minus, they are state corresponding to two orientation of the indicator, and in order for the apparatus to clearly distinguish between the two states, we need that the two orientation are very different, and we can naively translate these by saying that the overlap between the corresponding states is about 0. Now, what happens in reality is not that as soon as the interaction is activated, the state became orthogonal, but they become exponentially fast orthogonal, and so we can say that this happens in a very short time. So now we got this interaction that says that there is an entanglement between the system and the apparatus, but this relation has a problem, and to see this problem we have to consider another basis of the apparatus that we call A tilde, and we have to express this state in this new basis. So we have that A plus minus is C plus minus plus A tilde plus C plus minus minus A tilde minus. And if you plug this into this expression, we get that alpha plus times C plus plus A tilde plus C plus minus A tilde minus plus beta minus, and here we have C minus plus A tilde plus C minus minus A tilde minus. And now if we isolate the A tilde terms, we have A tilde plus that multiplies alpha C plus 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 beta C minus plus minus, and the same for A tilde minus. We have C plus minus alpha plus C minus minus beta minus. And now if we make the particular choice of this coefficient C such that this product is plus 1, this is plus 1, this is plus 1, and this is minus 1, we recognize here the state 0, here the state 1, and so we get 0 A tilde plus 1 A tilde minus. And so what we conclude is that we have rewritten this expression as this, where we still have an entanglement, but between another basis of the system and the apparatus. And so this consideration makes clear that there is an ambiguity about what is the operator of the system that we are measuring. But this ambiguity is only apparent, and it will vanish because if we consider some properties that the apparatus has to satisfy in order to measure the desired operator, that will bring some constraint over this interaction, and the constraint over this interaction will remove the ambiguity. So we need to find this constraint. The idea to find them is to state that we want this entanglement that is established by this interaction to be kept in time. So this means requiring that this entanglement is solid respect to the time when the collapse of the wave function happens. And so how we can state this formally? Well, the idea is to say that if we have SI, that is a state of the basis of the system that we want to measure, times an initial state of the apparatus, the evolution operator must map this into a state where this acts only on the apparatus state. So in a state like this. In this way, the entanglement between this basis and the apparatus is kept during time. But this expression is only for one state of the basis. If we now consider a general state, so we have sum over I of alpha I Si A0, and we apply the operator UDT, we end up with sum over I alpha I Si AI. And if we call this psi and we consider the density matrix of psi, we find sum over ej, alpha I, alpha j star, si, ai, sj, aj. And now what we can do is to consider the reduced density matrix of the system, that is the trace of the degrees of freedom of the apparatus of ρ. And as we said that the state of the apparatus become fastly orthogonal, if those states are orthogonal, we can calculate the trace over this basis, and so this is a sum over k of ak, ρ ak, and if we plug this inside, we have sum over I k j, alpha a, alpha j star, si, and then we have ak ai, the bracket, but as those are orthogonal, we have delta I chi, and then we have sj, and then we have delta jk, and so we are left just with the sum over k of alpha k modulo square sk, and this is a diagonal matrix where the diagonal entries are these values that do not depend on time, and the diagonal entries of the reduced density matrix of the system are the probabilities of finding each state of the system. So what we conclude is that if this is the way the apparatus and the system interact, then the probability of finding each state of the system does not change in time, and this is a reasonable properties that we expect in a measurement process. So now let's go back to this relation and let's write this more formally. The idea is that, as we said, this operator acts only on this, so it commutes. We can say that it commutes with the states of the system, of the basis we are trying to measure. So we say that U commutes with the operator si for every I. So now this U is the evolution operator, so it is related to the full Hamiltonian that contains every free term and every interaction term. But the idea is that reasonably during a measurement experiment, what happens is that the interaction between the apparatus and the system is an interaction that is very localized in time. Let's think about like a particle passing through a detector. But this interaction establishes this strong entanglement between the state, the system, and the apparatus. So this means that this interaction must be very strong. And so we can neglect, during this time span of interaction, all the other Hamiltonians, and so consider this U as e to the minus 1 I over h bar HSA, so only the interaction between system and apparatus time. And if we use this expression, this commutator can be expressed as commutator between HSA and SI is 0. But now, if we consider an operator whose eigenstate are the term of this basis where we are that we are trying to measure, it can be written as a sum over the basis of the eigenvalues of the basis si, and so if this holds for every I, it implies that HSA commutes with this operator that in the case of our example is sigma x. And so we have found a relation that the interaction between the system and the apparatus has to satisfy in order to measure a desired operator. But the fact is that this relation is not enough, because there could be more operators that satisfy this commutator. And so the idea is that we need another relation to remove this ambiguity. And to get this other relation, we have to think that over the apparatus and the system, there is even more in the universe. And so there is an environment that interacts with the apparatus with an Hamiltonian HAE. And now the idea is that with this relation, we showed that the probability of finding the states of each state of the system doesn't change in time. But as the system is entangled with the apparatus, we can ask even that the probability of finding each state of the apparatus do not change because they are the same. And in order to, as we said, just something very similar, we can write a relation similar to this, but related to the probability of measuring the states of the apparatus, by saying that the Hamiltonian of interaction between the apparatus and the environment commutes now not with the state of the system, but with the state of the apparatus. And if we want a relation of this kind, we can define the projector over this basis, and then say that the Hamiltonian of an interaction between the apparatus and the environment commutes with this projector. So now we have two relations, and we expect that these two relations remove this ambiguity and select just one basis of the system. So so we have this kind of the interaction between the system and the environment generates this kind of entanglement only for one special basis of the system, or equivalently one special basis of the apparatus, as there is a correlation between the two. And in the literature, this basis is called the pointer basis. Pointer basis because if we think about the apparatus, these states correspond to the different orientation of a macroscopic pointer. And so there is only one pointer basis, and this pointer basis is selected by this interaction Hamiltonian. And in order to select, in order to choose what is the pointer basis, so to choose what is the operator we are measuring on the system, we have to design the apparatus such that we tune these to interaction in order to satisfy those relations. So these two relations answer the first question: how should we design our apparatus in order to measure a desired operator? Now let's use these results for the second part of the discussion, that is to give an operative description of quantum measurement. To give an operative description of quantum measurement. What do we mean by operative? We mean that we will explain the results, the statistics of the result of an experiment, but not what happens to the state of the universe when we make the measurement. So, in order to get this operative description, let's consider a particular setup. And this particular setup is that we have some particles prepared in this superposition of plus minus that go into a Stern-Gerlach device, and then here we have two other Stern-Gerlach devices but that operate in reverse. So here we have minus plus, minus plus. So what happens at this stage? At this stage we have that this Stern-Gerlach apparatus couples the plus state with this trajectory. So we have plus times r minus, that is this trajectory, while the state minus the state minus is coupled with the other trajectory. Then we go into these other two Stern-Gerlach apparatus, and if we consider this one, it is reached only by the packet with minus, so we can consider only this state. And what happens at this stage is simply that this trajectory is changed with this other trajectory that we call r tilde minus. So at this stage the state will be plus r tilde plus minus r tilde minus square root of 2. And then we have a point here where those two trajectories cross, and here we will have the same here the two packets are on the same position, r0, and so we have the same state of the beginning. So here, if we consider the density matrix of the system, it will be plus minus r0 times plus minus r0 over 2. And as this is the state is separable, the reduced density matrix of the system will be just plus, plus minus, plus, plus minus over 2. And this has all the combination between plus and minus, so it is a matrix that has 1, 1, 1, 1. Now let's consider instead to make a projective measurement at this stage of the position. What happens if we make a projective measurement of the position is that we some particles will collapse in this state and some other particle in this other state. So what we will have at the end is a classical mixture of the two states, and so the reduced density matrix will not have off-diagonal element, but will be 1/2, 1, 1, 0, 0. So the two density matrices are different, but is what we expect, because the reduced density matrix of the system contains all the information that we can extract from the system through some experiments, and we expect different results from experiments where the particles are in a quantum superposition or in a classical superposition. So now the challenge is to use the formalism we developed before in order to get this reduced density matrix, but avoiding the projection measurement. And it is that we can do that easily by considering the fact that we said that the interaction between the system and the apparatus generates an entanglement. So we have that the state plus minus over square root of 2 times an initial state of the apparatus becomes plus a plus minus a minus over 2 over square root of 2. And we said that these two states become fastly orthogonal. And if those two states are orthogonal, we have seen before that when we compute the reduced density matrix of the system, we will get something that is 1/2, and here we have 0, 0, and on the diagonal we will have the coefficients that we call the alpha I square, that now are 1, so we'll have 1, 1. So we will have the same reduced density matrix that we get considering a projective measurement, but without considering a projective measurement. So now we have to consider the fact that we know that this entanglement happens only for one special basis, that is the pointer basis. So in order to get the same reduced density matrix that we get considering a projective measurement, we have to design our apparatus such that the pointer basis is the basis of eigenstate of the operator Sx. And we know, because we calculated it before, that we have to satisfy the two relations that I cancelled in order to have the eigenstate of Sx as the pointer basis. And so here we showed an operative description of quantum measurement, because in this way, as we get the same reduced density matrix, we can explain the statistics of any experiment without avoiding the concept of projective measurement, but it's only an operative description because we can say anything about what happens to the full state of the universe when the measurement happens.